Well, it might still be worth it. If there's any children who, I've just been saying to Yogi that if somebody wants to tell the children, I know they're a little distance away, but they might enjoy the flight. So I was preparing it with children in mind. So if there's any person who could just send a message to the young people, I'd be grateful if they could be perhaps at least told that it's on. I didn't realize the children weren't here. While some of them may be coming, I'll tell you a little bit about flight. I've always had an interest in flight, and I'm going to talk to you specifically about feathers. And I'm going to have some young ones, if we've got them here, to actually take part in this talk. So I do need the children if we can get them. So it'd be nice to have them if in fact they can come back. I've often had a keen interest in aviation, and it's part of my interest in fluid flow, part of my interest in heat transfer, mass transfer. Doing anything to do with fluid flow and heat transfer involves aviation. It brings it all together basically, because you've got to know what you're doing in things like that. I worked a bit on the Tornado, which is now no longer used, but it was used for a long while in the British Armed Forces and the Air Force. And we did all sorts of work in wind tunnels, as I'm showing you here. We used wind tunnels to test aerodynamic forces on these new aircraft. And then I ended up lecturing in heat transfer and combustion, leading my own research team. I specifically looked at acoustic waves, which is pressure waves, and I'm going to refer to that tomorrow morning when I'm going to talk to you about the human voice. That's going to be my talk tomorrow. I'm going to talk to you about acoustics, but that's not my talk today. I'm going to talk to you about aerodynamics and particularly about feathers. I'm afraid a lot of these books have now gone, but the big book on creation, which I did with Stuart Burgess, you can, if you know that you are interested in it, then I'm sure we can get some more copies to Norway, and that would be great. And there's all sorts of things on birds and flight in that big book. I love going to air displays, and I've passed a critical year this year. I won't tell you what it is, but you can guess. And my wife is going to said, okay, do you want to go to an air display? I said, yes, please. So we're going to go to an air display. I'll just, I love looking at the man-made aircraft, and this is also some American ones, just for my friend Danny, just to show him that, you know, I do sometimes look at American ones. And I will admit the Blue Angels are pretty spectacular. I'll just play you a clip, if I can, of this. This is the Blue Angels, the F-18s, doing amazing formation flying. And then it gets really horrendous when they do this bit. Watch the one on the bottom right. You've got two aircraft coming straight towards each other. I'm following one of them, then straight across. Just incredible. So some really impressive stuff. Well, it all began, of course, with those two guys. You all know who they are. Yeah, the Wright brothers, that's right. And the clever one was Wilbur on the right. He really had a very, very clever mind. And you can guess what he did in order to get aviation to work. He actually copied the birds. And he understood. He actually did wind tunnel experiments where he actually measured the forces very carefully of different aerofoils, different curved surfaces. And of course, they had to have bowler hats to do their work. I don't know why. That probably kept their brains warm, because it was pretty cold in North Carolina. It's not quite where our friend Danny comes from, but it's a bit north of there. And it was on a very cold December day, December the 17th, 1903, when the first man-powered, first flight took place, where it was powered flight, and it involved control. Other people had done it, but they hadn't controlled the aircraft. They controlled it very carefully, although it did crash right at the end of the day. Anyway, did you know that, of course, when it comes to birds, you're not using any of these artificially made surfaces. You're not using metal. They were using canvas and ropes when they built the first aircraft. Birds, of course, use feathers. And this is just utterly staggering what birds do. Because as you may realize, every single feather is different on a bird. Did you know that? Every single feather is totally different in some way to even its neighbor. And it's usually how much it's curved. Now, these are common gull feathers. This is a feather from a buzzard. And I'm going to demonstrate something. And I would like Jenny Marie, if you come up and just show me or do what I asked you to do. Right, I'm going to do it first, and then you can see how it's done, right? I'm going to separate the barbs on a feather, right? So I've got here, you can see, because you've got very keen eyesight as a child, and you can see it's very, very furry inside on both sides. Now, when I go back like that, okay, something remarkable is going on. Because if you do it carefully enough, I didn't quite do it. It just needs a little bit of help. A bird usually has an oil, which it gets from a gland down here, and it actually, no, it's not to being rude. And it covers the feathers with oil, and then you see it's all back again. Okay, so you do it just to show that it's not my magic. Okay, see? So you can now run your finger over it and you can actually get it to come back together again. Isn't that remarkable? So the feather has an amazing mechanism. Thank you, Jenny Marie. If you'd like to just sit down again. And I'll tell you what's going on. First, I'll come to it. I'll actually do that again. If we get some more children coming in, I'll just do it once more so that they can see it. Because it's really quite remarkable. No two feathers are the same. And all birds, of course, have a different arrangement. Some have large feathers, some have small feathers, some have coloured feathers, like this kite feather here, beautiful browny colour. Then you get, in our country, we have kingfishers, and my friend Colin Mitchell took these pictures, absolutely wonderful. Just sort of see the incredible detail that he's got of this. And of course, they are great fishers. Even if there's a no fishing sign, they'll carry on because they can't read English and they just get their food. And there you are, he's got his catch, as you can see on the right-hand picture. Now, when those F-18s that I was showing were doing the air display, or whichever aircraft you're looking at, you've got to be able to have some sort of surface to turn the flow. I was saying to Danny earlier, that whatever means you use to turn the flow, it doesn't matter. You could ionize the gases, right, and get a great big magnet and turn the flow, and then that would cause a force on the magnet of an equal and opposite reactionary force, which is Newton's. Come on, were you listening to Danny? It's Newton's what? Which law? Which law? I'll give you a hint. Newton's third law. And that's what I taught my students when I was doing aviation and teaching them basic aerodynamics, that actually, although you can put it down as Bernoulli's equation and all the rest of it, actually it all boils down to Newton's third law, that if you turn the flow, there's got to be a reaction on the thing which is turning it. And in this case, it's an aerofoil. So you could go into all the details of what the force is. And of course, you need to be able to control that turning of the flow. Now, of course, with birds, you're dealing with not with metal, you're dealing with feathers. So we'll build up the wing with feathers. And then, of course, that has to mean that not only as you look down on the wing, you've all got different feathers in different places, and no feather on any bird is the same as any other. Right? Right down to a little hummingbird, all the feathers are in exactly the right place, all doing their function, not only looking down on the wing, as I showed you earlier, but looking sideways on the wing to make this shape. Okay? If you don't think I'm right, look at this white-tailed eagle, which I took in, there's some wonderful bringing back from Scandinavia here of white-tailed eagles into the Isle of Mull. off Scotland, and they're gradually multiplying. They used to be there years ago, now they've been reintroduced. And so you go out on a fishing boat, and the chap, fools the eagle to come in and catch the fish and puts a dead fish in the water, and then you can set up your camera and you can actually see it swooping down to collect its prey. It thinks that it's going for a live fish, it's really a dead fish, but it doesn't matter, it still goes for it. But the beautiful aerofoil shape, you can see it there, see the top surface, that is real first-class aerodynamics. Wonderful forces going on there. This picture shows it even more. As you can see, the steep curvature of the leading edge of the wing. That's how an eagle, and every aerodynamic surface in birds, even the small little hummingbirds, are doing exactly the same. They're turning the flow. My friend Colin Mitchell has taken these even more superb pictures of red kites. They really are magnificent birds. And they've been reintroduced to Wales, and there's a large number of them now. They even come up to dirty Manchester. Sometimes we see them flying around. And it's not so dirty now, actually. Andy Burnham, the mayor, has made it a bit cleaner. But that's a wonderful picture of a red kite coming in for collecting its meat, which is provided at Gigrin Farm. You can see them doing it. But here's some other birds. This is gannets. This is another gentleman I know, took these pictures. St Kilda in Scotland. And here's another one. I love this series of pictures he took of birds changing, these are gannets, changing the shape of their wings as they come down like pencils to grab the fish off the coast of St Kilda. Here's another bird doing the same. This is a peregrine falcon in a dive called a stoop, and it's going at 200 miles an hour in a dive. It does 200 miles an hour. And it's got special transparent eye covers in order to protect its eyes. It's not the fastest bird in level flight. The fastest bird in level flight is the swift, which can fly at 70 miles an hour, or, sorry, I should be using kilometers, which is about 112 kilometers per hour in level flight. That is pretty fast. And it's got specially shaped wings in order to do that. I think the bird that I really, really love seeing is the hummingbird. I had the tremendous privilege of spending a couple of weeks in St. Lucia back in 2020, just before COVID hit. We didn't know what was coming. And these were pictures I took of the Antillean crested hummingbird. It's got this beautiful crest on top. And it's beating its wings so fast, you have to put this on a very fast shutter speed in order to get it. And it's actually beating its wings in the region of 100 to 120, somewhere in that region, 120 times per second. And hummingbirds are just utterly marvelous acrobatic flyers. This is another hummingbird in a different location. So this was up in, I can't remember where it was, up in Oregon. And it's actually I forget now the name of this hummingbird. It'll come back to me, but it's quite common, ruby-throated hummingbird. It doesn't look ruby because it's iridescent. It's got to get the reflection to get the red. Here's another picture of the same hummingbird. There's the ruby-throated one. And these hummingbirds actually achieve their flight by actually bending their wings like this. This is what hummingbirds are doing. They actually have a special joint such that the shoulder can swivel right over 180 degrees. It's unique to hummingbirds. And they don't move the wrist. Basically, the wing for any bird is actually the hand, which is much elongated. And then there's the radius and the ulna here. And although there is a shoulder, it's very, very short. And they barely move the humerus. All the movement is really from the elbow or the equivalent. And so a hummingbird is doing this motion, right? So it's actually beating its wing 100 or so times per second. It will be over 50 and less than about 120. Sometimes in very special occasions when it's doing a courtship dance, it can actually beat them even faster than 150 times per second. And it's actually doing this motion such that the tip, you can see, is doing this. It's actually beating its wing such that it's turning it right over and then bringing it back up again. So it's beating it twice per cycle downwards because it's using the upper surface in a downward stroke. Do you see what's happening? And so that motion means, and insects do the same. It's both a pronation and a supination when you're twisting upwards, okay? And it's doing this both sides. And if it does one side slightly different to the other, then it moves sideways. Or it can, of course, actually turn itself almost over itself and go backwards. And hummingbirds do it so fast. You have to have a very fast movie camera in order to pick up what's going on. And this little video just shows you a hummingbird taking off, and it shows you the twisting motion that I was referring to. That's the motion that I'm referring to. It's beautiful little bit of footage. Sometimes the BBC really does do things right, just occasionally. And here's another set of pictures just to explain this figure of 8 motion. And of course, what the point I wish to make, coming back to feathers, is that every tiny little feather on a hummingbird is also in exactly the right place, as I said earlier. Just while we're on hummingbirds, they have very long tongues. And you can see the tongue just protruding into the nectar of this plant. And the tongue comes out, as you can see there, about 5 to 10 times per second. So while the wings are beating, as I said, of the order of 100 times per second, okay, the tongue is going out 5 to 10 times per second in order to get the nectar, which is why I just love these birds, because they are just extraordinary. They have to eat their own body weight every day, right? And they eat, of course, they drink or eat nectar, and that's how they get their food. Now, of course, if we were to eat our own body weight every day, I don't think we'd last long, some of you particularly. Oh, I shouldn't say that. But this is the Antilles crested hummingbird that I mentioned that I saw out in St. Lucia. And it's a very, very small hummingbird, and you could just see the tongue coming out there. Just rather lovely. Just to show you, though, I won't show you the actual film because it will take too long and I will keep you from your lunch, from your dinner, rather. But it's recently been shown that the hummingbird's tongue is not what you think it is. You would have thought that it was a straw. No, it's not. And you would have thought that they suck the nectar up. No, they don't. It actually, the tongue splits in two, right, once it hits the surface of the nectar, and it has a series of little cups which open, right, and basically grab little bits of nectar in their little cup. Then as it retrieves its this separated part of the tongue, these close up and bring the nectar into its throat, and it's happening 5 to 10 times per second. So it's a very complicated system. It's not what you think, and that's only recently been found out. And so it's absolutely extraordinary what's going on. So really, the findings about the tongue show that everything must fit all together. If you wish to go onto the Discovery Institute website, or the Institute of Creation Research website, both of them talk about hummingbirds. Frank Sherwin has done a lovely article on the ICR website talking about hummingbirds by design, and you could get hold of that. So just to say that really this is an example of interconnected systems, or you might say, as some people use the term, irreducible complexity. In other words, you haven't just got one system that you need in order for this bird to function correctly. You've got to have many functions working together. You've got to have this incredible structure, which I'm going to now talk to you a little bit more about, which is on the feathers. And you've got to have this mechanism for the hummingbird with the separated tongue with these individual little cups. To suggest that this evolved is frankly nonsense. It's everything is telling you as an engineer, and I come at this with an engineering mind, a mathematical mind in some places, and I'm saying this is shouting design, because you've got layered systems which all have to be working together. So did birds come from reptiles? No way. This is a picture of a lizard out in Africa, South Africa, when I was there. Yeah, wonderful creatures, but frankly, nothing like birds. So when somebody said that feathers emerged from, the feather has the same fundamental structure and development as a reptilian scale, there is total nonsense, because the keratin, which is what feathers are made of, yes, you can argue that the keratin is the same as the keratin of something like a lizard or a reptile in some so-called evolutionary precursor. But actually, the keratin, frankly, is slightly different. But we'll give them that just for the time being. The keratin isn't exactly the same. But let's say that it is. Well, the issue is that scales on a reptile come from a totally different location on the skin. They're very close to the surface, as you'd imagine. There's a little bit underneath, but essentially it's growing very close to the surface. But not so a feather. A feather grows from a follicle, and a follicle is an incredible device. I've got a big pen here, and the feather is rather like this part which is doing the actual writing part of the pen, and growing in a sort of a sheath, and it grows in that, and the bottom of the sheath is connected to flesh and blood, which is giving it all the nutrients it needs in order to not only make the follicle, which is this, and the collar of the follicle, but to also make the feather grow inside it. So that's the actual thing that you see under the microscope. I've done a diagram of it here so you can see what's going on. You've got the follicle, you've got a growth collar, and you've got a feather growing inside the follicle. Now, it's incredibly thin. It's nowhere near the thickness of what I've showed you there. Just to give you some idea, here's a little video of it growing inside the follicle. Now, why do you have follicles? Well, because every feather has to go in exactly the right location on the bird's body. And it mustn't, if you've got two feathers growing together, imagine what would happen. They would interrupt each other, and they would destroy a very important mechanism which is keeping these barbs together, which I'm going to show you in a minute, right? What Jenny showed you earlier, I'm going to show you why that happens. Well, that mechanism would get sort of interrupted if these feathers were growing without a follicle round it. So that's very important. This illustrates on a young pigeon which fell out of a tree where we were living. Yeah, do come in, guys. Come in and sit at the front here. I'll show you what we're doing. Come in. Let these kids come and sit at the front. I'd love to have them. And I'll come to the front, some of you, because I'm going to repeat what I did with Jenny. What's your second name again? Jenny Mary. Jenny Marie. Yeah, I'm going to repeat it. So come, just one or two of you, some of you come and sit at the front, because I want to show you something. Right, that's really good. Thank you for coming. And I'm sorry if I brought you away from your beautiful, great games that you've been playing. But I'm just going to show you something. This is feathers growing on a baby pigeon which fell out of a tree, so we called it Humpty. Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. Well, perhaps in Norwegian you don't have it, but you can see here, this is the shiny bit is the follicle, okay? So that follicle is very, very thin, and as the feathers grow, then the follicle disintegrates and it just becomes dust on the bird. And when a bird molts, that's what you see on a bird wing. You can actually see the dust of all the follicles. But these are tubes. Sadly, this bird didn't last very long because we didn't know how to feed it. We've learned since. But we should have fed it on sugar water, but it didn't last very long. But there's no evolution of these, okay? Now, let me now deal with the issue of you come just at the right moment, because now I'm going to repeat the experiment. Can we have somebody else? Jenny did it very well earlier. Does somebody who's just, do you want to come? Sorry, what's your name? Oh, you're Lois, aren't you? That's right. Lois, do you want to come and do what your sister did? Do you want to come and See, now look, if I separate this out, this is what we did earlier, right? I can put it back together again. We're going to actually work out what's going on. Do you want to do it? Do the same. Hold it up so everybody can see. Yeah, that's right. Just put your finger in it. That's right. Separate it out. Doesn't matter. Now, if you put your... Jenny Marie will show you how to do it. Do you want to show your sister how to do it? Right. Look, you see, you can put it back together again. Yeah? Now, what is going on? It's amazing. You know, you don't need something complicated to show that evolution is really just a nonsense explanation. Because now I'm going to show you what really is going on. A feather is a marvel of lightweight engineering. This is made of keratin. In fact, it's hollow. And it's so light, right? And yet, it's very, very strong. Because this is the rachis, right? This is called the rachis, which is the center bit. And these that you can see are called barbs in English. I don't know what they would be in Norwegian. Okay, so these are probably barbs, but there we go. I don't know. But these are barbs, okay? And what we're now looking at is, in detail, what happens is that not only are there barbs, which are these, there are barbules as well. Barbules, which are mini barbs, okay? Mini barbs. And so in between these two separated barbs, I've exposed, if you look very carefully, have a look at it, if you look very closely, pass it along so everybody can see. And we could do it with another one here. You can actually, but you need a big one really to do it. But you can actually see a bit of a furriness, which is what we're now going to refer to. Because the barbules going that way are different to the barbules going that way. So if you've got two adjacent barbs, right, they hang together because the barbules coming from the barbs this way have hooks on, and the barbules coming that way have ridges on. So the hooks slide over the ridges. Some of you folk, I shouldn't be sexist here, but it's usually the ladies, will make curtains to go on windows, okay? And so you have a curtain rail, okay? And you have hooks which slide over. The men can do it as well, but usually the ladies are far better at doing it. They're much better engineers, really. They know what they're doing. The fellas just look at it and say, oh, how do you do this? But, you know, but you've got the hooks sliding over a ridge. Right? Thank you very much. And this is a feather of a buzzard, by the way. I don't know, where's the other one gone? I think that was a gull feather. You still looking at it? Where's you passing it round? No, pass it round. You can pass this round to the other children at the back. In other words, the adults. Yes, Joachim.
It almost sounds like Velcro.
It is. Well done, Joachim. It's exactly that. Except the only difference is that whereas Velcro has brushed nylon all over the place and hooks on one side, this has ridges, right, such that it slides and keeps the barbs together. Even as the barbs are moving, right, I've got a feather here, the big one's gone to be shown to others, but as I do that, obviously there is a sliding motion going on. You've got it. That was bright comment. You've got a movement going on, even as the barbs are moving. So you can imagine a bird using this and the feathers moving in the air, right? But the barbules are keeping the adjacent barbs together. That is just incredible. How did that come about? Such that, you know, some odd lizard was fraying its scales and it said, oh yeah, I must make sure that I've got a barbule going in one direction which is different to the other. Oh, that's nonsense. And in fact, Richard Dawkins was asked the question, where did this come from? And he was caught. Here's some other pictures. David Menton, who's recently died, sadly now. He's gone to be with the Lord, which is far better for him. But he took these wonderful pictures. And there's another diagram of it. And just to show you that in supposedly 99 million year old amber, which is hardened resin from a tree, I don't think that's 99 million years old at all. That's not my position. I believe that all this was made probably at the flood. But amazingly, you've got the same structure in supposedly very old feathers. In other words, God always made them exactly as they are. But here's a little video. We can perhaps just time to play this. I hope we have. Oh dear, have I run out of time already? Where are we? What is the time? I can't.
Exactly.
Oh dear, I'm meant to be finishing. When did I start? Can I have a bit more time, Yogi?
You can have 5 more minutes if it's...
5 more minutes. When am I meant to be finishing? Now?
You started late, so take some little
Oh dear, I didn't know the time had gone.
Richard Dawkins has written at great length about genetics and has committed much of his academic career to answering the questions that arise from Darwin's theory. Something has to explain the novelties themselves.
Well, the novelties themselves, of course, are genetic variations in the gene pool, which ultimately come from mutation and more proximally come from sexual recombination. There's nothing very inventive or ingenious about those novelties. I mean, they are random. And they mostly are deleterious. Most mutations are bad. And so you really need to focus on natural selection as the positive side, and it's only natural selection that produces living things which have the illusion of design. The illusion of design does not come from the novelty.
What was it
Listen to
about
this.
that early novelty, before it culminated in something as useful as a feather? Where could natural selection get its purchase upon something which was no more than a pimple?
There cannot have been intermediate stages which were not beneficial. There's no room in natural selection for the sort of...
He's digging a hole.
Foresight argument that says, well, we've got to persist for the next million years and it'll start becoming useful. That doesn't work. There's got to be a selection pressure.
In other words, he doesn't know.
So there isn't a process, as it were, going on in the cell saying, look, be patient.
No.
It's going to be a feather, believe me.
Yes. It doesn't happen like that. There's got to be a series of advantages all the way in the feather.
But there
if
is
you can't think of one, then that's your problem, not natural selection's problem. Natural selection, well, I suppose that is a sort of matter of faith on my part, since the theory is...
You get it? It's incredible. He dug himself a hole and fell right in it. It's a beautiful quote, that is. And as I've shown you, feathers have always been the same. Okay, right. Let me now ask you a question. I've had special permission from Yogi to just go on slightly further. And do you want your tea? Well, if you want your tea, go and get it. But the rest of us will watch this. Okay. Right. But I just want you to see how amazing owls fly, right? Now, owls fly extremely quietly. And I'm going to show you something which only has come to light in recent experiments, not by me, but by others. But it really is remarkable. I'm going to show you this little clip from super-powered owls. Again, the BBC actually pulled off a good one on this one, okay? There's no evolution in their discussions in this bit. Right, have a look at this.
Good girl. Moses. Mo.
This is a falcon. And this is the owl.
Shh. It's Kenz's turn. Shh.
No, nothing at all. Absolutely quiet. It's amazing.
But what have the microphones picked up? The decibel waveforms show the sound being generated by the birds in flight. Each spike is an individual wing beat. But with the barn owl, there's almost nothing. Even our array of super-sensitive microphones failed to pick up any sound of Kenza in flight.
And here's the owl doing exactly the same. Nothing. Nothing at all. I'll play it again.
Okay, well, the secret is in the amazing structure which is both at the leading edge and the trailing edge of the feathers. There is a comb and a fringe arrangement which removes the turbulence which normally comes from when you get lift. So there is a comb. If you look at an owl feather, it's deliberately serrated at the leading edge of the wing. So this is not an owl feather. I'm afraid I haven't got one with me. But if this were an owl feather, then you would see a serration going down there, right? Which is at the leading edge. And then you've also got a comb structure on the trailing edge as well. It's a sort of a fringe. So that is the secret as to why the owl has such quiet flight. And it really is an amazing creature. It also has stereoscopic vision. It also has very, very sensitive ears, which are not, by the way, placed in exactly the same place on each side. One of them is higher than the other, which means that it can actually comb, well, I'm using comb in a different sense. It can pick up sound in the longitudinal direction as well in the latitudinal direction. So it's got very sensitive ears, very sensitive eyes as well. So this is the leading edge comb that I was referring to, and then the trailing edge is this sort of serration that I showed as well on the back end. So there's no evolution here. And in fact, this has become the inspiration for making wind turbines a lot quieter. So again, it's an example of biomimetics, where nature got it right. Well, that means that there really was brilliant design there to begin with. And this has been picked up by engineers who are trying to make wind turbines, which are a little bit noisy at times and sometimes a bit ugly. I'm not sure I'm a great fan of having loads of them, but that's the way things are going. And if we can make them quieter, that is not a bad idea, because they do interrupt people's lives. So what they've done is they've put a serrated edge here, which then controls, I'll use the technical term, it controls the boundary layer, and then it breaks up the vortices, which you not always get from flight. It breaks up the disturbed air such that it doesn't make as much noise. So it really is frankly amazing. Time really won't permit me to do this last bit properly, but just to say that some feathers have wonderful colours, don't they? I've got here a peacock, or part of a peacock feather. It's got a little bit damaged in its travels, but it is really rather beautiful. And the eye of a peacock feather is frankly amazing. Can I just say this bit? It really is amazing. These are the barbs that I refer to, but these are not flight feathers. They are show feathers, right? But the way they make colour is amazing, because partly in the peacock, the colour comes from pigment, partly, but not entirely. By pigment, I mean that there is actually some chemical in the barb itself. But please note that as this barb grows from the rachis, which is here, it's got that colour, then it changes to this colour, and then it changes back to the colour we had before. And this is growing. This is living. This barb is growing. So there is a system which is saying switch on the colour, switch off the colour. Now that's not all. What about this colour? Well, that colour is not formed by pigment. The greens and the turquoise and the blue are formed by, listen to this, iridescence. And iridescence is a colour which comes by reflection. It's nothing to do with pigments. And it's an incredible issue, because you actually see it by having two surfaces, right, two very thin layers together, which bend the light, okay, and then cause the light to be reflected, and the white light splits now into, it's really made of red, orange, yellow, all the way through to violet. And as we heard earlier, red has a different, lower frequency to the violet, which is much higher frequency, and of course that means shorter wavelength. And that means that the blue bends at a different rate to the red, which is why at some angles you see blue, some angles you see turquoise, and it makes for a very beautiful shape. But this means, this is just incredible. This means that this barb, right, has got pigment in it. Switch off the pigment, this is in real time as it's growing, and now change to an iridescence, right, which is to do with split layers, you understand me, right? It's a different system, right? That's used here. Then please switch that off, now changed back to pigment, right, and then carry on. And it's just frankly amazing. And all this must be programmed in the bird, right, simply that the peacock could show a wonderful display to a female, which in the main totally ignores it. If you've watched a peahen with a peacock, there's not an awful lot of sort of, ooh, isn't it lovely, you know, basically. Well, there is a bit, I guess, but I frankly think that it's there because God wants to show us his glory. In fact, Darwin said, the sight of a feather in a peacock's tail, whenever I gaze at it, makes me sick. Basically, Darwin was saying, I can't really understand why the peacock should have such an incredible display of colour. And, well, as I showed you, there's iridescence even on these Antilles hummingbird that I showed you earlier. And when you get it in the right light, it actually began to show colour, iridescence on its little crest. It was absolutely beautiful. You have to see these birds to act. And there is, I won't go into it, but there is a marvellous shape here, which is using what we call the golden ratio. So I'm going to end. Job chapter 40. Yes, sir, I'm just finishing. Job 40 says, I've put this in the Old English, so I need to put it in more modern English, really. Have you an arm like God, or can you thunder with a voice like him? This is God speaking directly to Job. Deck yourself now with majesty and excellency, and array yourself with glory and beauty. We have a wonderful lesser-spotted peacock there, red-throated hummingbird. And then time won't permit me to tell you of the Wilson's bird of paradise, which is frankly really beautiful. These birds are just extraordinary. And God is saying to Job, can you do that? And of course we can't. We might be able to understand what's going on, but we cannot come anywhere near the glory of what God put into creation. Even in a fallen world, God has put a marvel of demonstration of his beauty. This, of course, supports very clearly Romans 1:20, which says the invisible things of God are clearly seen, being understood by the things that are made. But as I close, can I just point something out? Because the evolutionists will come back and say, but what about the nature red in tooth and claw? Some of the birds you've been talking about, I didn't actually directly refer to their habits, but the red kites are birds of prey, and they will feed on other creatures. Well, we need to be reminded that the world isn't what it was created as. Why? Because we sinned. Adam sinned, and sin has a price to pay for us, which but also it has affected the creation. And we need to be aware of that. Young people here, you need to be aware of it. You need to be aware that we are no longer living in a world which is like it was to begin with. And we need to be ready with an answer to give to those who say, this world is a nasty place. And indeed, they're right. Orcas, we were discussing in the car, killer whales, they play with seals in a horrible way before they finally gobble them up, which is not a very nice thing to see. But God has made a remedy. The very creator who made everything also came to this world, as you know, to bleed and to die on a cross. And we haven't seen the end yet, because that same Saviour, if we trust him, can make you into a new person. He died to take my sin, and if you trust him, he died to take yours as well, right? But that isn't even the end yet. He's going to come back again, and he's going to restore this world. I don't know all the detail. Ask Yoga, he understands these things. Or ask the gentleman who was preaching this morning. His name's gone from me. Ask them. They understand because they've studied it. But I don't know all the detail, but I know the Lord Jesus Christ is coming back, and he's going to make a new world wherein dwells righteousness, and it's going to be perfect, and it's going to be even better than the original creation, and we'll never die. Isn't that wonderful? God has a future for this planet, you and me, if we believe in the Lord Jesus Christ. Thank you, Yogi. You've been very patient.
Thank you, Andy. Thank you very much.
You can see why I wanted the young people.
Absolutely.